we were trying to combine functions, and again, there's like 7 main type. This is not too difficult. You have your linear. The domain is XER, YER. The range would be YER. It exists everywhere. What about a quadratic? What's the domain for a quadratic? X squared. It exists everywhere on the domain, but on the range, it has to be strictly greater than 0. Yeah, like that?
Mm-hmm.
X squared is very, very, very similar to the absolute value of x. They share a lot of properties. The domain and range is the same for both of these. This is the absolute value of x. And then you have the square root of x, which looks like this. Domain is that x cannot be negative. You can't have a negative number inside a square root. And if you look at the graph, y also cannot be negative. So they're both strictly greater than 0. And then we have an exponential function. Doesn't matter what the base is. The domain is going to be XER. The range is going to be y strictly greater than 0. And then you have your sines and your cosines. Goes through the origin. It's an odd function. This is sine x. X is valid everywhere, but the range is restricted between -1 and 1. Same thing with cosine. The properties are very similar. It's just that cosine doesn't go through the origin. This is cosine of x. This is XER. And again, the range is the same between -1 and 1. What am I missing? Log function looks like this. X has to be strictly greater than 0, but y can be anything. Exponential function and log functions are the inverses of each other. So these are the 7 main functions. And if you just have an idea what they look like, then you can come up with the domain and range. What else do we do? We're combining functions. We're doing f plus g or f minus g. F and g are 2 independent functions. The combined function will have a domain where f's domain and g's domain, they intersect. Like if f goes from -infinity to +infinity, g goes from -2 to +2, they're strictly intersecting right here. This is the part that they have in common. So the domain for f plus g or f minus g, you'll see this later, f times g or f divide g, doesn't matter. As long as you're trying to combine your functions, the domain is going to be where both of them intersect. This is an important idea here. If one of them is infinite, like the first one up here, then it's going to resort to the lowest common domain, which will be like the lower domains of between both of them. We'll do a bunch more examples here. Let's see. This one needs a graphing calculator. We can skip that. Let's just start with this one. So yesterday we were adding and subtracting. Today we're going to be multiplying and dividing, but the idea is the same. Instead of adding the y values, you're going to multiply them. The x values, they're going to stay the same. So let me do it like this. So we have our x value. We have our blue curve there, the quadratic. We have our red curve there. And we're trying to multiply them. We're trying to do f times g. So let's start over here. At an x value of -2, what's the y value of the blue curve?
-4.
-4. What about the red?
-2.
Yeah, -2. So when you multiply them, you'd get a +8, yeah? So look at this, the combined function f times g between these two, when x is -2, you get an 8, which is outside of the scale, but that's going to go all the way up here. At -1, you're going to do -1 times -6, so that'll be +6, right? At 0, you're going to do 0 times anything, well, that's going to be a 0. At 1, you're going to do 1 times -4, that's -4. At 2, it's not very clear. At 3, you're gonna do 3 times 6, 18. So it's gonna be like all the way down there. So your combined function would look something like this, okay? Let's just try one more. At -6 and -6, that'll be positive 36. Oh, no, sorry. We don't know the y value for the blue curve, so this is the only thing we can do. 6 times -4 is -24. So somewhere over there. So that's what the combined function will look like, as far as we know. A better way to do this would be to just straight up multiply them. So you want f times g of x. You can just take your f of x, you're going to multiply that with your g of x. So you have x, which is your g of x, times x squared plus x minus 6. You can open this bracket if you want, but you don't have to. You can leave it in the factored form. Let's factor this. Two numbers that multiply to -6 and add to 1, what are they? It's 3, right? And -2, like that. Multiplies to -6 and adds to +1. So what we have here is a cubic function, okay? That graph was not very good because I didn't use this point. So here we have a linear and a radical square root function. Part A. What's the answer to part A? It's just a one-step thing. It says find f times g of x. You're given both f and g. You just multiply them, right? Look at this. It's very easy. It's just a one-step thing because you can't factor a radical. So for A, they want f times g of x, right? Look at this. We were given f of x, given g of x, straight up just multiply them. F times g of x is going to be equals to square root of x, that's your f, times, in a bracket, what your g is, like this. You can open your bracket if you want. You don't have to because you can't really factor a radical. So you can just leave it as it is, okay? Leave it as it is. How do we do B? It says find f times g of 4. In part A, it said find f times g of x, but now it says find f times g of 4.
You plug in 4 as x.
Yeah, so it'll be square root of 4 times 1 over 2 times 4 minus 2. It's going to be 2 times 0. It's 0. And that's it. Easy peasy. Part C, find the domain. All right, so now this is where you have to use your thinking caps. What's the domain of a linear function, g of x? Does it have any restrictions?
No.
No, so we have an XER for the linear, right? So -infinity to infinity. So this is for g of x. What about for a square root of x? What's the domain? I'll give you the graph, right? Just remember, there were 7 of them. Square root of x looks like this. What does it look like the domain is? Can it be -1?
No.
Can it be 0?
Yes.
Yeah, so it goes strictly from 0 with a closed circle all the way to infinity. So where do these two graphs intersect? The domains. By that I mean the domains.
0 to infinity.
Right, so the combined domain, again, one of them is infinite, so as you go to the lowest common domain, it's going to be 0 inclusive to positive infinity. That will be the combined domain of f times g, okay? And then part D says use graphing technology and discuss the key characteristics. All right, so we could do this by hand, but we're not going to, because you can't really see a trend for bigger numbers. 0.5x minus 2. All right, so here's the graph. Notice how it does not exist, right? Beyond 0, because square root of x is not valid. Is this function increasing or decreasing?
Increasing.
Yeah, in the long term, it's increasing. It's because it has a positive slope and square root is also increasing. But from here, look at this, from here to this vertex here, this function is decreasing, okay? Initially, it dips a little bit. Why does it do that? It dips a little bit because the y-intercept is negative. Because that initially it dips, but after like a few steps, because the y-intercept is going to come above the x-axis, it becomes positive, and then it's going to fly all the way to infinity and beyond. And that's it for that one. This question looks difficult. But how hard could it possibly be? All right, so we're given the concentration of some contaminant, C of t, where C is the concentration, T is time. And then we're given the rate at which the water leaves the sewer in cubic meters per second. Determine the time at which the contaminant leaves the sewer and enters the lake at the maximum rate. Yeah, we know we're multiplying them because this entire unit is multiplication, but what's happened here is that, what is this? This is some water. It's contaminated, okay? And the concentration of contaminant is given by the first equation. And then the same water is gonna exit from a sewer, okay? And the rate is given by WT, 1 over t to the power of 4 plus 20. Now the question asks, determine the time at which the contaminant leaves the sewer and enters the lake at the maximum rate. What do we know about maximum rates? What does it mean by maximum rate? It's talking about the slope, right? Rate just means slope. So it's asking us, when are we going to have the maximum rate, okay? When is the slope the greatest? Cool? When is the slope the greatest? I think they might have used a graphing calculator. They always do this, which is kind of cheating, but whatever. It's the idea that's important. So for this, what you do is step 1, you're gonna find the total contaminants in the lake. You're gonna do this by first finding the total contaminants in the sewer times the rate at which the sewer exits into the lake, which is gonna be WT. So you get t squared over t to the power of 4 plus 20. When you multiply this with 1, you get t squared, and this has a denominator of 1, you just get t squared plus 20. So that is the total contaminants that's going into the lake. The question is asking us to find the maximum, okay? It's asking us to find the maximum. For this, I guess you do need a graphing calculator. I'm gonna steal their graph. So if you were to graph this, you would get, it appears you would get a peak right here, yeah? And the peak says x equals, this is the x value at the peak, 2.11. So that's the answer to this question. The time when its maximum is going to be 2.11, and you're done. Usually you won't see a question like this on the test because you're expected to graph well, I guess you could graph this because we know there's gonna be a horizontal asymptote at y equals 0 because the degree in the numerator is less than the degree in the denominator. But whatever, we're not super concerned with this. Let's go down here. And this is very similar to the thing that we did yesterday. The combined function is only going to be valid where both of them have the same x values. Okay? Where both of
Mhm.
them have the same x value. Let's look at a. What's the answer to a? 0 comma what? We're multiplying them.
-2.
Yeah, -2. 5 times -2, 10 for 1, 21 for 2, and 12 times 5, 60 for 3. And you're done, right?
Mhm.
Okay, let's look at b. 1 comma 6 exists in F, does not exist in G. Can we delete this?
Yes.
Yes, it's gone. 1 comma 6 is gone. What about 4 comma 1?
You can get rid of it.
It's gone. See you later. What about both of these?
You can get rid of them.
So these are also gone. So we are only left with 2 points. So the answer is 0 comma 12 for the first one. And then you have 2 and -20 for the second one. And that's the entire answer for B. What's the answer to C and D? They're both one-step answers. What's the answer to C? Just multiply them. What's x times 4?
4x.
That's it. That's the entire answer for C. What about D? What's x times 2x?
2x².
Yeah, done. And same thing for E, right? You just multiply them. For F, it's just going to be 2 to the x times x minus 2. There we go. Working with these is not easy because, like, let's say you had 2 to the power of x, x minus 2 equals 4. How do you solve this equation? It's not very simple. Yeah, but we don't have to solve the equations. We're just trying to come up with the properties of these guys. Let's look at these two. They're both radical functions, square root functions. We're asked to come up with the domain. Here, let's look at this one by one. This is why being able to graph this is very important, because that gives you the domain, even if you don't know what it is. Square root of x, okay? Here, let me show you. Looks like this. Keep this in mind. Square root of x looks like this. If anything is inside the function, like these ones, they're gonna move it either left or right. If you have x plus 1, like this, the form you're comparing it with is this. This is called the transformation using the point mapping rule. We did this a long time ago. But what happens is plus 1, you would expect it to go to the right, but it goes left because just like the x-intercepts, everything is opposite. So x plus 1 actually takes it 1 unit to the left. So the graph of 1 plus x looks like this. It's the same thing as this one, except it's moved 1 unit left because of the plus 1. So this is what the graph looks like for f of x. 1 plus x. For g of x, it's slightly more difficult because of the negative sign in front of the x. So for g of x, you can rewrite this as negative x plus 1, step 1. If you compare this with its transformation rubric, and transformation is the same for any function. You have a, which is the amplitude or the vertical stretch, times f is the function k x minus d plus c. So here a doesn't exist, so you can ignore it. A is 1. F is the square root function. C doesn't exist, you can ignore this. K is always the number that's being multiplied with x. Here, what is our k value? Something times x gives us negative x. What's our k value?
-1.
Negative 1, right? So k is negative 1. You have to pull that k value out because everything has to be in this form. So I'm going to pull this out. What am I left with if I pull out a negative 1 from this? X plus 1 or x minus 1?
X plus 1.
It'll be x minus 1. Negative times x, negative x. Negative times negative 1, positive 1. So you need to be able to do this to see what the transformations are. So now what does this mean? You notice k is negative 1, yeah?
Mm-hmm.
But d is 1. If you compare this minus 1 with minus d, d is 1. If d is positive, it's going to go to the right. So again, we're going to start off with our parent function, square root of x. K being negative 1, or this negative sign, it's a reflection on the y-axis. It's like putting a mirror on the y-axis and seeing what you get. This is what you're going to end up getting. Right now, we have square root of negative x, okay? Square root of negative x. You always have to do reflections before you're allowed to move it upside down or left, right. So first, we're going to use k as negative 1, reflected on the y-axis. Then this minus 1, what this does is it's going to shift because d is positive, it's going to shift to the right. So the final graph is going to look like this. At 1, it's going to start, and it's going to go this way, okay? Like that.
Mm-hmm.
So that's the graph of g of x. Where do the domains intersect? Look at those two graphs. Where do the domains intersect? If you want to do this on a number line, f exists from -1 to positive infinity. This is for f. Whereas g exists from +1 to negative infinity. Like this. So where are they intersecting? What do both of them have in common?
-1 to 1.
Right, so that is going to be the combined domain of f times g, or f plus g, or f minus g, or f divided by g, okay?
Mm-hmm.
It's where both of them intersect. So it's going to be -1 is included because they can both be -1 and they can both be +1. So let's double check this. So that's our hypothesis. It's going to be from -1 to 1. We're just going to type these in and multiply them and see what you get. 1 plus x times, I don't know why that's 2, times 1 minus x. And if you notice, look at it. It's like a little circle, right? It's a semicircle, correct?
Mm-hmm.
There we go. And that's what we expected. Combined domain is always going to be the intersection between two domains. Let's make this a little bit more complicated, because if you understand this, you should have no issues doing any of these. But you do have to know transformations and what the parent function looks like to come up with the domain. But I'll help you. What's the goal here? The goal is f times g. You just multiply them. It's super simple. Nothing too fancy. Let's look at A. What's the domain of f and what's the domain of g? They're both linear functions, right? X minus 7, x plus 7. Slope of positive 1 for both of them. What's their domains? What's the domain of a linear function?
Negative infinity to positive infinity.
Exactly. So what's going to be the combined domain?
The same.
The same, 1 and done. What about b? It's a square root function. The plus 10, is it going to move it to the right or to the left?
To the left.
To the left, correct. So it's going to start at negative 10, okay? It's going to start at negative 10 and 0. Both of them. So what's going to be the combined function? What's going to be the domain of the combined function? So f looks like this, right? Negative 10. G is the exact same function. It's also going to look like this. So where do the domains intersect?
At 10.
Yeah, so the combined domain is going to be negative 10 to inclusive to positive infinity. Yeah, the
Mhm.
same thing, because that's where the domains intersect. This is very weird though, because if you look at x plus 10, you multiply this with x plus 10. You know, if you multiply two different square roots that are exactly the same, you get root x squared. This and this cancels out, you get an x. The square root simply disappears. You would get x plus 10 squared, and you would get x plus 10 because the square root cancels out with the squared. So this is what you are left with. What's the domain of this? It's a linear function. It's a domain of a linear function.
Negative infinity to positive infinity.
That's right. Now this is where things get tricky. So what's the answer to B? Is it this? Because this is what is simplified to? Or do we look at it from the original function's perspective, giving us this as the result? Which one do you think is right? I'll give you a hint. This one doesn't take into account the originals, whereas this one does.
The first one.
The first one is right. We don't care about the simplified stuff. You have to take into account where it came from, okay?
Mhm.
Because these two functions don't exist beyond negative 10. So you can't get something from nothing. So over here, this would exist at negative 11, but it's not in the mathematical domain of the original functions. So this one would be correct. So you're always gonna look back to where you started. C is
Mhm.
easy. They're both polynomial functions. One of them is quadratic for C, one of them is linear. What's the combined domain for C? They're both polynomials. Well, it's going to be XCR because if you look at 7x squared, that's a quadratic. It is only valid. It's valid everywhere. Same thing with the linear, x minus 9. It's valid everywhere. So the domain will be XCR for the combined function, okay?
Mhm.
The answer is exactly the same for D. What's the combined domain for D?
XCR.
Yep, done. Now E is where things get interesting. So what does a 2 sine x look like? Again, remember, sine goes through the origin unless there's a horizontal transformation. Here, there's no d value. 2 sine x looks like this. The maximum will be 2 because in the parent function, the maximum is a 1. You just multiply that by 2. The minimum will be negative 2 because negative 1 times 2. And sine x always goes through the origin. So it's going to go like this to 2, come down like this, and it's going to go forever, okay? It's a periodic function. It's going to loop back and forth forever and ever and ever. So that's a bad drawing of 2 sine x. What about 1 over x minus 1? 1 over x was one of the functions I was missing. This is what 1 over x looks like. It's a reciprocal function. This is your d value in here, x minus 1. Compare that with x minus d. Does it go to the left or to the right, that minus 1?
To the left.
It goes to the right.
To the right.
Yeah, because x minus d is the original. So 1 over x minus 1 looks like this. There is a vertical asymptote at x equals 0 on the y-axis. So this vertical asymptote is simply going to shift 1 unit to the right. So the graph would look something like this. At 1, there's a vertical asymptote. Now look at these two sketches. What's the combined domain? The sine is valid everywhere, and the reciprocal function is valid everywhere except for the vertical asymptote. So what's the combined domain? There's only one restriction. Got to think about the LCD because one of them is XER, so just go with the lowest common domain between them. It'll be everywhere except for 1, okay? Because the domain for the sine function is XER. The domain for the reciprocal function is XER. X cannot be 1. If one of them is valid everywhere, then the combined domain will be the lower of the two, will be the more restricted of the two. So the combined domain is also going to be this. Cool? Does that make sense?
Yeah.
Let's graph this because it's always helpful to visualize things. So 2 sine x, I don't know why I wrote 6. So that's our first function. And 1 over x minus 1, that's our second function. We kind of had an idea what both of them look like. Now let's multiply them. Is there a times function here? Yes, right. That didn't change anything. Now let's go to the x value of 1, if it'll let me. It does not let me, does it? Oh my god. There's like an infinite points right there. Look at it. Kind of cool. Can you give me the point for 1? Well, it wouldn't, so it doesn't really matter, but there you go. Okay. At 1, we know it's going to be invalid. It's not in the domain. There's probably going to be a hole or something there. Don't know why you can't see it. Kind of would have been kind of nice, but there's just too many points here, so it doesn't really matter. Let me see if I can do something here. You go from -5 to 5 at a step of 1. Let's see if this does anything. No, was worth a try. But anyways, we know that the combined function is going to exist everywhere except for exactly at 1 because one of the functions is not valid there. Yeah? Kind of makes sense? If it's not valid, it just doesn't exist. What about f? This one. What's the domain of 2 power x? Sorry, yeah. What's the domain of 2 power x? It's an exponential function. If you want to sketch 2 power x, anything power x looks like this. What's the domain of this?
Negative infinity, positive infinity.
Right. Log x plus 4. This is what log looks like, log of x. There's a vertical asymptote right here. The plus 4, does it move it left or right?
Left.
Left. So it's going to look like this. Now there's the vertical asymptote. Remember, it will never touch the vertical asymptote. X cannot be -4. At x equals -4, there's a vertical asymptote. So what's the combined domain? If one of them is x,
-4 to positive infinity.
yeah, done. Is -4 included or is it excluded?
Excluded.
Done. Easy peasy. Okay, that's all.
Mhm.
That is all. This one is slightly more difficult. So sec x is the reciprocal of sine, cosine, or tan. It is a sec.
Cosine.
Cosine is right. Cosine looks like this, okay? We're just gonna do maybe like a 1 cycle here. At 0, it's a 1. At 90, it's a 0. At 180, it's -1. At 270, it's a 0, okay? And at 360, it's a 1 again. So what does sec x look like? Wherever the y value is 0, there is going to be a vertical asymptote. When you're trying to do a reciprocal function, whenever the y value is 0, there's going to be a vertical asymptote. So sec x ends up looking something like this. Let me use a different color. So notice sec x cannot be 90 degrees, right?
Mhm.
Cannot be 90 degrees. And then it cannot be 270. And this cycle, it's going to repeat. The next one will be 90 plus 360. It'll be at 450. Every cycle, it's going to repeat. The next one will be 270 plus 360. What is that, 540? 270 plus 360. It's 630. Like this. It's going to repeat. In fact, it's going to repeat every 180. After every half a cycle, it's going to have a restriction, okay? So I'm going to write this as 90 plus 180k, where k is some integer. K is any integer, 1, 2, 3, 4, or -1, -2, -3, 4. So that's the restriction for secant of x. 90 degree initially, and then from there, every 180 degrees, left and right. What about for this function? Does this have any restrictions? For this, you'd have to factor it. Here, why don't you try it? Two numbers that multiply to -14 and add to -5. What are they?
-7 and 2.
-7 and 2 is correct. So this thing is going to factor out to x minus 7, x plus 2. So what can this function not be? What are the restrictions for this guy? You got to remember that you can't have a 0 in the denominator. What value of x would make this a 0?
7.
7. So x can't be 7. What about for this one?
-2.
-2. So x can't be -2. So now look at this. The combined domain, okay? X can be anything. It cannot be 7. It cannot be -2. And it cannot be any multiple of 90 plus 180k. So what that means is there's going to be a bunch of asymptotes here. That's at 7. This is at -2. There's one at 90, and then from here on, there's one at every 180. So over here, 90 minus 180 is negative 90, like that, and then every 180. It's gonna look something like this, okay? It's gonna have a bunch of vertical asymptotes everywhere. Kind of makes sense?
Yeah.
Let's graph this. Let's see what that looks like. It's always interesting to see what a combination of function looks like. Just times what am I multiplying this with? X squared plus 5x minus 14. It looks super weird. It looks something like this. I don't even know how to describe this pattern. But don't worry, you don't have to know how to graph this. I don't think it ever ends. But you can make a lot of funky stuff with the functions that we already know. I think once upon a time I showed you Desmo's art, if you remember that.
Mm-hmm.
Let's see, there's a new one here. Submissions open. I don't want to see the submissions. Why don't you show me 2022. All right, let's look at this. Let's look at this grasshopper or whatever. We have a linear function right there. You see that?
Mm-hmm.
We have a quadratic. We have a cosine. That looks pretty good. So you don't have to know how to do this, but people just do this in their spare time as a hobby. So that was the first question. It's going to exist everywhere except at these points. B is a little bit easier because the exponential function is valid everywhere. What about the log function, that -8? Does it move it to the left or to the right?
To the right.
To the right is correct. So log of x minus 8 at 8, it's going to look something like this. 99x is valid everywhere. So what's the combined domain? It's going to be the lowest of the two, right? This one's only valid when x is greater than 8. 99x is valid everywhere. Yeah?
So 8 to positive infinity.
Yeah, so it'll be -8. Sorry, +8 to positive infinity. Cosecant x is very similar to sine x, sorry, secant x. It's not going to be valid at 0 degrees, and then from there, every 180 degrees to the left or right. Z means their integer. So the first one is going to be at 0, it's not valid there. From there, it's going to be invalid at every 180 degrees to the left and the right. So that's for cosecant x. Does this plus 81 move it to the left or to the right?
To the left.
To the left. So it'll look like this. What's the domain of this function?
-81 to positive infinity.
Right, so it's -81 to positive infinity like that. So what's the combined domain? This one's going to be slightly tricky. It'll be -81, okay? That's where it's going to start because this one can go all the way to -infinity, but we're restricted at -80. It's going to be -1 to positive infinity, except it cannot be anything that's a multiple of 180, okay?
Mm-hmm.
That'll be the lowest common denominator. For this one, for the log function, you have to look at it like this. It'll be x plus 3, x plus 3. What can this not be? What value of x can it not take?
-3.
-3. What about something that's bigger than -3? Let's say -4. I think that's fine. It just can't take -3.
Mm-hmm.
What about this square root function? What can it not take? So in a square root function, let me show you this to you from both perspectives. Inside of a square root function, this thing has to be bigger than or equal to 0, yeah?
Mhm.
So if you look at the graph, x squared minus 1 looks like this. When is this function greater than or equal to 0? We're looking at the y values. So in other words, for which x values, okay, for which domain or for which x values is the graph above the x-axis? Can x be 0? Look at the y
No.
value. No, it says below. What about -1? Can x be -1?
Can't.
Yes, it can, because if x is -1, then we are equal to 0, right? Because it'll be -1 squared minus 1. So that'll be 1 minus 1. That'll be equal to 0. We're good. So look at this. The domain for this function is going to be to the left of -1, inclusive, and to the right of +1, inclusive. Because that's when it's bigger than or equal to 0 for this function.
Mhm.
We're going to do the same thing with this guy. X plus 3 whole squared looks like this. It's moved 3 units to the left at -3, okay?
Mhm.
We know this thing inside of a log function, it has to be strictly greater than 0. So if you factor this, you'll see that it's going to be greater than 0 everywhere except at exactly -3. So that was our domain. That was right. This is our domain for the weird looking square root function. What's the combined domain? So this one is valid everywhere except at -3, right? This one's valid at x equals -1. So the combined domain is going to be x can be less than -1. X has to be bigger than +1 because of the restrictions for the first one. But then x cannot be -3. That'll be the combined domain. That's where they intersect. And that'll be the answer to this question. Okay?
Mhm.
Kind of tricky, this one. Hmm. What does a negative do here inside the square root? It's a reflection. It's gonna be a reflection on the y-axis.
Mhm.
Okay, -1 means it's a reflection on the y-axis. What's the domain of this?
0 to -infinity.
Yeah, -infinity to 0, lower bound, upper bound.
Mhm.
What about log x plus 10? The plus 10, what does that do?
You shift to the left.
Shift to the left. Now there's gonna be a vertical asymptote at -10. It'll look something like this, okay?
Mhm.
So what's the combined domain?
-10 to 0, but -10 is exclusive.
Correct, yeah, that's perfect. So it'll be -10 to 0. Provide two different strategies. Well, you can sketch them and you can kind of be like, hey, there's a 0 here. What doesn't matter what the y value for that is. 0 times that is 0. Okay? It's like, looks like it's 2 or something. 2 times 2 is a 4. There's a 0 here. 0 times anything is a 0. Yeah, like that. This is a bigger negative value than this. Positive number times a negative number will be a bigger negative number. Bigger negative number. So I'm assuming the graph would look something like this. Let's sketch it and find out. But the domain is correct. The graph is always a little bit tricky if you don't have precise numbers. Times log of x plus 10. Let's see what that looks like. Yeah, kind of on the money there, right? Kind of has a peak there, and then it's gonna follow this, and it's gonna repeat this vertical asymptote all the way to negative infinity. Cool? At negative 10, look at it. Where did it go? It said it's undefined because at negative 10, our function is undefined, yeah? There's a vertical asymptote. That's why it was inclusive. Negative 10 was not included in our domain. So the strategy will be just to sketch them individually and then multiply the y values. This one is weird. It says determine the equation of f of x times 1 over f of x. So there we go. Can we cancel out the x squared minus 25s?
Yes.
Yes, so the entire thing is 1. So y equals to 1, again, remember this. Y equals to any number is a horizontal line that has a slope of 0. The domain of this horizontal line is XCR. Now this is the tricky part, okay? This is the domain of our final answer. Question is that the domain of our combined function? What's the domain of x squared minus 25? It's a quadratic.
It's just negative infinity to positive infinity.
Yeah, so this one has no restrictions. What about 1 over x squared minus 25? Does that have any restrictions? The answer is yes, right?
Can it be 5?
Can it be negative 5?
No.
No, so x cannot be positive or negative 5. Now, where do these two intersect? Well, if you have XCR for one of them, that means you gotta go with the LCD. So this is going to be the combined domain, okay? So that means if you graph this, okay, if you graph this at positive 5 and negative 5, you'll see that there's gonna be a hole over there because the function cannot exist in that portion. Let's see it. So even though the final thing has XCR domain, one can be valid everywhere. Plus 25 times. Basically, the point is you always have to consider where did the original functions come from. Look at it, it's a perfect horizontal line, yeah? But I don't know if this will give it to me. Please give it to me at 5. No, it's obviously it's not going to give. At 5, there should be a hole, okay? At exactly 5, there's going to be a hole. And we know that because of this. There's a restriction on this. We don't care about the final result. What we care about is where do the functions, where do they originate from? All right, let's call it a day there. Next time we're going to do some dividing. It's the same idea. It's just with something over something.
Okay, thank you.
See ya.